We're excited to present to you our project for CS 8903 this semester, Spectra, which is a systematic processing, evaluation, configuration, testing, retrieval, and assessment system. Spectra is a novel multi-agent framework which uses large language models to validate cloud configurations. Our system addresses limitations of existing single agent approaches and single LLM approaches, employing specialized agents that collaborate to come up with a solution. Today, we'll be going over the motivation behind this project, our proposal, our methodology, some results and analysis, as well as our conclusions. So let's start with the motivation. Ultimately, software cloud misconfigurations are a huge threat and a huge issue. They're a leading cause of system failures, security breaches, and data leaks. And modern complexity in cloud infrastructures, human mistakes, and the rapid evolution of these systems makes these configurations over 60% of the time the cause of cloud security breaches. So ultimately, it is very important for us to be able to mitigate the risks of these situations. Several solutions have been explored in the past, right? Manual testing, rules-based systems, but these are very error-prone and non-scalable since they involved often a human in the loop or more time-consuming. Our system is scalable and effectively manages cloud configurations due to the dynamic nature of cloud environments and sophistication of modern attacks, and is resilient to these. So the power of LLMs ultimately is that they're able to understand complex patterns. LLMs are trained on a vast amount of data, and they have a lot of ability to understand these complex dependencies. Additionally, LLMs are good at generalizing. They can generalize patterns across a diversity of configurations, no matter their structure. Thus, single LLMs are limited, though, because they don't understand these complex dependencies. And they don't have access to real-time context or up-to-date information about documentation. Furthermore, single LLMs are susceptible to hallucinations because they may not have the exact sort of context and may just make up facts. So ultimately, multiple LLMs working together can overcome these, and that is the power of our system. So here's our proposal now. So Spectra, as I mentioned, leverages multiple LLM agents that can cooperate and coordinate in order to solve this issue. Each of them has a specific role, and each of them takes part in a broad range of activities in order to ultimately determine if a software configuration is valid or not. This is more effective, and it provides actionable results related to misconfigurations. So here are our key contributions in this study. Firstly, as I mentioned, we propose a multi-agent configuration validation framework, which we use Microsoft's AutoGen package to deploy. Each of the agents has a specific task, for example, content gathering and chunking using retrieval augmented generation, coordinating and reporting the outputs. We also run statistical tools like Terraform validate command, specifically for Terraform configurations. And finally, we also include reasons for errors and warnings, as well as suggestions for fixes, and stating the assumptions of the LLM. Beyond this, we also contribute a real-world Terraform dataset, which is helpful to ensure the robustness of our system. Terraform is a widely used configuration framework today, and so thus we made sure to evaluate our framework on these types of data. Lastly, we do a comparative evaluation and benchmarking across a variety of LLMs, some small and some larger, and we assess performance metrics, including F1 score, precision, and recall, providing insight into why we selected and deployed certain models and which one gives us optimal performance.
Now let's talk about the broad architecture of the system. We have several agents that work sequentially, like validator, QA, Terraform validator, and reporter. And these specific agents can have their internal monologue to achieve a task. So on the left-hand side, you can see the validator agent. We give it a couple of examples of configurations and the configuration to input. And it then goes to large language model and asks its internal training data to validate it. Its response is then passed to reporter agent. The QA agent specifically validates using the services documentation. So we provide the configuration to validate, and the documentation URL. The content gatherer then goes on the internet, parses the documentation, creates chunks based on that, and gives the relevant context to the configuration analyzer for each property. The configuration analyzer then analyzes based on the documentation and gives the results back to QA, which it then formats and passes to reporter agent. And in the case of specifically Terraform, we are also running a statistical tool called Terraform Validate. For that, we spawn up a Docker container and run the Terraform configuration within that. And then the log parser agent looks at the logs and checks whether the configuration is valid or not. All three inputs are then passed to the reporter agent, which decides which output to keep. So if QA agent is very confident in its approach, the reporter agent keeps its output, otherwise it switches to validator agent's output. And for Terraform specifically, uh, we prioritize that output because uh, it's given from a statistical tool. Next, please. So now we'll talk about methodology a bit. We tested this for 11 open source different kinds of configurations, and we added Terraform as well on top of that because it's widely used, and there was no paper that did that before. We tested this on 5 different large language models. Some of them were big, some of small. For the data set, we used OpenCTest, which has been a standard for configuration data across the papers. And for Terraform, we manually collected the data and injected it with errors, but more on that later. For metrics, we're using F1 score, precision, and recall, and we are doing that on file and parameter level. On parameter level, we actually go and look at how many parameters were miscategorized or categorized correctly. And our benchmark currently is the Siri framework that uses only a single agent LLM. Next, please. To collect the data set, we looked at the GitHub repositories, which at least had 100 stars, so they're reliable, and then parsed them and manually collated the data based on that. And once we had a valid data across different kinds of services, we then injected the errors manually to create a test and training data set. Okay. Now look at some of the results. These were the hyperparameters that were used for each run. We tested for total 138 types of configurations for each LLM for various services. And for each run, these are number of properties, and these are valid and invalid examples we gave to the LLM and the RAG chunk sizes. Next.
So on this table, we show the file level metrics, both for the baseline as well as for our system. Ultimately, we see some very interesting results here, namely that the best performing model is actually a little bit of a smaller one, Claude HiQ. And this was a bit of a surprising result, but one that was also interesting to analyze. Beyond this, we also see that this best performing model had an F1 score in the average of 0.68, which is slightly better than the baseline. Ultimately, we can conclude here that the multi-agent system improved over the single agent system on the file level. Now on this slide, we show the parameter level metrics. Again, Claude HiQ in our system achieved the highest parameter level F1 score of 0.63. And ultimately, we show that there is consistent improvement with real-time documentation to better understand those parameters, which is something that our system provides. Next slide.
So the very first item that we refer to in our architecture is the config validator. Our config validator is very similar to what CD uses. We use a single LLM to ask configuration errors through the few shot mechanism. In our experiments, we use, similar to CD, the 2 valid and 2 invalid configurations as examples that you see on the top as a prompt, and then you see the example of those responses, very similar to Siri, that we received. This is one set of information which is used into the final reporting analysis. Now, contribution part of our work where we are using the retrieval augmented generation mechanism to look at the latest context and the content specific to configuration, documentation, and version. And we are gathering the content specific to the configuration that we are analyzing. And part of this work, we also deployed a configuration analyzer agent who is picking this gathered content and analyzing the configuration into the configuration file and identifying any misconfigurations and producing results. In case of Terraform configurations, we also deployed the executor, which looks at the configuration and validates it using the external tool. We spawn a Docker agent, and it basically executes this configuration and spits out whether the configuration is valid or not, along with based on our prompt, the answer that you see on the right bottom here. So eventually we get the the similar results as our QA validator is providing us, and this is another feed into our final reporter agent. So reporter agent finally looks at the input from different agents, specifically from config validator. It looks at the QA agent where the data is coming based on the content gathering and configuration analysis, and then third is a Terraform executor, and then it deploys a mechanism of picking based on the priority the right misconfigurations. It utilizes the confidence score in case of QA agent. In case of Terraform configuration, if we get a result using for the Terraform configurations for the Terraform validator, then we prioritize that over other agents. Now, comparing Spectra with CD, we see kind of a major upgrade in terms of the information, actionable information coming back from Spectra. It kind of reveals that we get more context for users about misconfigurations, including warnings, the suggestions for doing these fixes, and the assumptions made during the analysis. This really helps users to really addressing these misconfigurations beyond just the errors findings. A good example could be like the security warnings that typically get missed out by CD. So towards the conclusions here, while we see that while Spectra demonstrates promising potential, still some limitation exists in its current implementation. And we aim to address these in our future work. Specifically, we want to address the API rate limits. This area is evolving for the LLM models, and as the new models come with the better rate limits, we can do more comprehensive and deep analysis. Second, we would like to have a version of the model where we have human in the loop and have an ability to get the feedback from human and learn from that as well. Third is assigning. So we want to assign the confidence scores based on the log probabilities returning from LLMs. Currently, we are utilizing most of the LLM's own assessment about its confidence. We also want to expand the Terraform validator and executor to other type of configuration. Right now, it is limited to only Terraform configurations. And during our retrieval augmented generation, where we pick up content, where we gather the content, we are using in fixed size chunking mechanism, and we want to explore more agentic chunking as well as the semantic chunking as some advanced ways of finding the right size of chunks.
So ultimately, what are the key findings of our work? What are the big takeaways? Multi-agent frameworks offer a viable solution that address a lot of the limitations of single agent LLM approaches for configuration validation. Beyond this, it's important to address resource constraints and data availability for deployment of such systems. We've also learned through this work that incorporating external tools, knowledge, and sources of documentation, as well as advanced prompting techniques, can significantly help our validation accuracy. Furthermore, multi-agent frameworks can scale to meet additional configurations without human intervention. Finally, agents can leverage LLMs and provide additional actionable insight about misconfigurations by also providing warnings, suggestions, and assumptions for further analysis by a human. Conclusion, Spectra is a novel multi-agent framework for configuration validation, leveraging the power of LLMs and collaborative agents to address the challenges of cloud misconfigurations. And ultimately, by incorporating these additional sources of knowledge, as well as advanced prompting, Spectra does provide a robust and reliable solution for addressing the security and stability of cloud-based systems. Thank you all for listening to our presentation. Please reach out to us if you have any questions. Thank you very much.